Hello everyone, welcome to Sjctnc content. This is Dr.L.Jethruth Emelda Mary, Assistant Professor in Mathematics, St.Joseph College of Arts and Science, Autonomous, Cuddalore. In this video lecture, I am going to discuss about trees in graph theory for second MSc Mathematics. First, we'll define what is tree. We already know that a graph is called connected if there exists a path between every pairs of distinct vertices. So here, in order to define a tree, we need a connected graph. A connected graph without cycle is known as a tree. That means a graph, or you can say that is a connected acyclic graph is called a tree. Suppose a group of trees is known as a forest or means then each component is called as a tree. Now we have a theorem. This is a necessary and sufficient condition for a graph to be a tree. The statement is a simple graph is a tree if and only if any two distinct vertices are connected by a unique path. Here we prove this theorem in two cases by assuming the first converse part. Let us take T is a tree and prove that two distinct vertices are connected by a unique path. So this can be proved in contradiction method. Suppose there are two paths exist between two distinct vertices u and v. But we know that their union always contains a cycle in T. But T is a tree, so this is a contradiction to our assumption that two paths exist between two distinct vertices u and v. Therefore, there should be a unique path between every pair of vertices in a tree whenever G is a tree. Okay. Then the converse path. In this case, we assume that any two vertices of a graph G are connected by a unique path. Then we must prove that it is a tree. Here, since there exists a path between every pair of vertices, therefore you can say G is obviously a connected graph. Okay. Then clearly G cannot contain a cycle because there exists only unique path between two pairs of vertices, therefore it has no cycle. Since any two distinct vertices of a connected graph has no cycle, therefore definitely G will be a tree. Hence the proof is over. The next theorem says every connected graph contains a spanning tree. Before proving this concept, let us recall the definition of spanning tree. A spanning tree for any graph is nothing but is called that is a spanning subgraph. A spanning subgraph is connected as well as it has no cycle, means that is called spanning tree. So in this case, we are going to prove that every connected graph has a spanning tree. So let us take G is a connected graph and take C is a cycle, or you can say we can say that a collection of all connected spanning subgraph of G. But C is non-empty. Let us take T belongs to C. It's a fewest number of edges. If T must be a spanning tree of G means then definitely there is nothing to prove. In case the subgraph T is not a spanning tree, that definitely it would have contained a cycle of G. Then the deletion of any edge of this cycle will give a spanning subgraph in C having one edge less than that of T. This contradictions leads to the choice of T. Therefore, T has no cycle. Hence, therefore, this T is always a spanning tree of G. The next theorem is the number of edges in a tree on n vertices is always n minus 1. Conversely, a connected graph on n vertices and n minus 1 edges is always a tree. Okay, the theorem says suppose there is a tree means if it has n number of vertices, then definitely n number of edges means definitely there will be n minus 1 vertices. So this is the concept of the theorem. So we shall see the proof now. Let us take the graph to be a tree now. We use the induction on n to prove this theorem. M is equal to, assume that m equal to n minus 1. When n equal to 1, we get m equal to 1 minus 1 equal to 0. When n equal to 2, we get m equal to 2 minus 1, that is equal to 1. So for these two cases, the result is true. Now we assume that the result is true for all trees on n minus 1. and or fewer or less than mm, n minus 1 vertices or n vertices. Let T be a tree with n vertices, and let us define a edge E is equal to UV be an edge of T. Then UV is the unique path in T joining U and V. Hence, the deletion of E from T results in a disconnected graph having two components, say T1 and T2, where T1 and T2 are connected subgraphs of a tree T. But both T1 and T2 form a trees. As number of vertices in T1, number of vertices in T2 are less than number of vertices in T. Therefore, by induction hypothesis, we may write the number of edges of T1 is equal to n of T1 minus 1 and m of T2 is equal to n of T2 minus 1 according to the statement in the hypothesis. Therefore, m of T is equal to m of T1 plus m of T2 plus 1, which gives n of T1 minus 1 plus n of T2 minus 1 plus 1. Finally, we get n of T1 plus n of T2 minus 1. N of T1 plus n of T2 is n of T minus 1. Hence, we proved m of T is equal to n of T minus 1. That is, number of vertices in a graph G, in a connected graph or a tree T, always number of vertices minus 1. Number of edges minus 1. Hence, result is true for T. Suppose, the converse part, suppose I assume G is a connected graph with n vertices, n minus 1 edges. Therefore, by theorem, previous theorem, you can say there exists a spanning tree T of G, and T has n vertices, and being a tree, it has n minus 1 edges. Therefore, G is isomorphic to T. Therefore, G is also a tree. Now, we have moved to the next theorem. A tree with at least two vertices contains at least two pendant vertices. That is, n vertices or vertices of degree 1. The pendant vertices means what? If the degree of a vertex is 1, that is called pendant vertices. That is also known as end vertices. Okay. Here, we are going to prove that a tree with at least two vertices always contains at least two pendant vertices. So, consider a longest path P of a tree T. What is T? T is a tree in which we have taken a longest path P. Then the n vertices of P must be a pendant vertices of T. So path means what? The alternative sequence of vertices and edges is called path. So definitely path which has two n vertices, the starting point, the terminal point, as well as the what is called the initial vertex and the terminal vertex, definitely will have a degree as 1. The vertex will have a degree as 1. Therefore, the path must contain two pendant vertices. Otherwise, at least one of the n vertices of P has a second neighbor in P. This gives a cycle in T, which is a contradiction. Hence, definitely the graph with at least two vertices will always have two pendant vertices. Next, we move to the corollary. If del of G is greater than or equal to 2, then G contains a cycle. So del of G means what? The minimum degree of G is greater than or equal to 2 means then the connected graph always contains a cycle. It is the proof goes like this. Suppose I take G as no cycle. Suppose G has no cycle means then definitely it will be a forest. Therefore, by proved theorem, the minimum degree of G is less than or equal to 1, which is a contradiction. Thus, G contains always a cycle. Okay. Next, we move to the next theorem. A connected graph G is a tree if and only if every edge of G is a cut edge of G. So, it is another obvious case that, or you can call it as a necessary sufficient condition for a graph. A graph is a tree means definitely every edges of G will be a cut edge. What is called cut edge? That is the removal of edge from the G, the graph G, makes the graph, the resultant graph as a disconnected means then definitely it is called cut edge. Okay. Therefore, every edge in a graph in a tree will always a cut edge of G. So, I'll take if G is a tree, there are no cycles in G. Hence, no edge of G can belong to a cycle. Each edge of G is a cut edge of G. Therefore, if every edge of connected graph G is a cut edge of G, then G cannot contain a cycle. So, these are obvious cases. Therefore, you can say that no edge of a cycle is a cut edge. Hence, G is a tree. The next theorem is a connected graph G with at least two vertices is a tree if and only if its degree sequence d1, d2, dn satisfies the condition sigma dn where I equal to 1 to n is equal to 2 times of n minus 1 with di greater than 0 for each I. So here d1, d2, etc. dn denotes the degree of the n vertices of the graph G. Here let G be a tree. As G is connected, then non-trivial and it can have no isolated vertex, hence every term of the degree of G is positive. Further, sigma I equal to 1 to n, di is equal to 2m. Already you know m is equal to n minus 1, so it's equal to 2 into n minus 1. Assume that the condition is true, then prove that the G is tree. So the converse part is obvious, so hence we prove the theorem. We move to the next concept. Lemma: if u and v are non-adjacent vertices of a tree T, then T plus uv contains a unique cycle. Here I'll take P is a unique, P is a path, or you can call it as a unique path, uv path in a tree T. Then P plus uv is also always a cycle in T plus uv. That is, by adding a edge in the tree T, new edge in tree to the taken graph T, means definitely T plus uv will gives a cycle, or will lead to a graph to be, make the graph to be a cycle graph. Hence P plus uv is a cycle. Since the path P is unique in T, then definitely T plus uv contains a unique cycle. So thank you for watching this video.